Hello and welcome to the Titus Timeout podcast. I'm Nick Searle, and in this week's podcast I will be discussing airflow calculation methods for displacement ventilation systems. Displacement ventilation systems can offer superior indoor air quality when compared to conventional overhead mixed air systems, and are suitable for a wide range of applications with large open spaces and high ceilings, such as theatres, hotel lobbies, shopping malls, airports and casinos. Displacement can also be very effective for ventilating school classrooms. The methods used to calculate the airflow rates are somewhat different to those used for a fully mixed system, and there are in fact two recognised calculation methods in use today, one published by ASHRAE and another described in the European REVA Displacement Design Guide. In this first of a series of two podcasts, I will be discussing the ASHRAE method. The ASHRAE procedure works on the principle that only a fraction of the sensible heat gains need to be offset with cool conditioned air, as a significant portion of the sensible heat is allowed to rise upwards out of the occupied zone. So this 5-step process starts with applying correction factors to the calculated sensible heat gains. The first step is to identify the type, location and magnitude of the loads and group them into these four categories. First, the heat produced by the occupants, here referred to as QO. The heat emitted by the equipment in the space, QE. Heat from overhead lighting, QL. And the heat from the exterior wall and window surfaces, which should include load transmitted through solar radiation, QEX. To demonstrate the ASHRAE method, I will use a 27-occupant classroom of 30 foot by 30 foot with one glazed perimeter wall and a 10-foot high ceiling. Step 1 involves identifying the sensible heat gains and breaking them out into the four categories. In our example, the occupant's sensible heat load for 27 occupants at 245 BTUs per person is 6,615 BTUs per hour. The equipment load, which includes items such as desktop computers and desk lighting, is 2,300 BTUs per hour. The overhead lighting load is 3,686 BTUs per hour, and the envelope loads due to conduction through the walls and gains from solar radiation is 10,800 BTUs per hour. The sum of all these sensible heat gains, TSHG, is 23,401 BTUs per hour, or around 26 BTUs per hour per square foot. Moving on to step 2 requires us to calculate the effective sensible heat gain by applying correction factors to the heat loads in the four categories, using multiplication factors taken from the ASHRAE Displacement Ventilation Design Guide. The corrected values are then added together to give a total effective sensible heat gain in the space, which is 5,105 BTUs per hour for the classroom. The required airflow rate can then be calculated using this formula, where ESHG equals the effective sensible heat gain we calculated in step 1, and delta THF is the maximum allowable head-to-ankle delta T, which is taken from ASHRAE Standard 55. The head-to-foot temperature differential should not exceed the recommended values to prevent discomfort, which is 5.4 F for seated occupants and 7.8 F for standing. As we are working on a classroom application, the occupants are seated for much of the time, so I will be using a 5.4 delta THF. So placing our loads into the equation, we get a result of 875 CFM. Step 3 involves checking to make sure that not only are the sensible heat gains satisfied in the space, but also the ventilation requirements for the classroom. Using this simple equation, which is shown on page 12 of ASHRAE Standard 62.1, we can calculate the outdoor ventilation air requirement for the classroom, where RP equals the outdoor airflow rate per person, PZ, the number of occupants in the zone, RA, the outdoor airflow rate per zone square foot, and AZ, the zone floor area. This equation simply adds a ventilation rate per occupant to a rate per unit of floor area to calculate the total outdoor airflow to the space. This results in an outdoor air requirement of 378 CFM for our example classroom. However, this figure must also be corrected for the ventilation effectiveness factor, known as the EZ number, which is shown on page 17 of ASHRAE Standard 62.1. As we are designing a low-velocity displacement system, the EZ number is 1.2. The reason for this is that displacement ventilation systems are more efficient at removing airborne contaminants, so less outdoor air is required compared to conventional overhead mixing systems. To calculate the actual ventilation rate required, we simply divide the VBZ number by the EZ number, which results in 315 CFM. So to arrive at our final total airflow rate for the classroom, we need to use the greater of the sensible load and ventilation requirement calculations, which is 875 CFM. In step 4, we will calculate the minimum supply air temperature to maintain the specified occupant temperature gradient using this formula, where TH equals the desired temperature at occupant head level, i.e. the room temperature set point. THF is the maximum allowable head to ankle delta T. A is the floor area. TSHG is the total uncorrected sensible heat gain in the space, while CFMSA is the maximum primary airflow rate, which was calculated in the previous step. So inserting the values into the equation results in a supply air temperature of 61.9 F. Finally, step 5 involves a simple calculation to determine the exhaust air temperature from the classroom using this equation, where TS equals the supply air temperature calculated from the previous step, TSHG is the total uncorrected sensible heat gain, and CFMSA is the total primary airflow rate. This results in an exhaust temperature of 86.6 F. Just to summarise, during cooling, our classroom requires 875 CFM of primary air delivered at 61.9 F, which is exhausted at 86.6 F. So that about wraps up the demo of the ASHRAE method. Don't forget to subscribe to our YouTube channel and look out for part 2, where we will cover the Reaver calculation method. Thanks for taking the time out with us.